Hi everyone. We often wonder in what direction AI agents or agents in general will go towards in the upcoming years. And we often think about that, and gladly so, people who are like ahead of us in this field have already tried to answer this question, and this is what we're going to discuss today. Today we're going to refer to the Alberta Plan for AI Research as a research paper by authors, of course, Richard Sutton, Michael Bowling, and Patrick Pilarski. Now, just as an overview of why I chose this paper, because it acts like a baseline philosophy on how AI research actually should go about in the upcoming years. Because we eventually don't want human in the loop. We want long-lived agents that actually are able to think for themselves without having any sort of input or any sort of nudge from the human side. And the core idea in this entire paper is basically reinforcement learning type environment, but the entire setup is same. We have the same observation, action, and reward, but the datasets are not fixed. You know, agents are operating in an open, non-stationary environment. This is something you should keep in mind as a constraint because we just want a dataset that acts or mimics the real life complexity. So we're also going to discuss we're also going to discuss the things that took time for me personally, like temporal uniformity, understanding how planning works in these cases, and how we have to just forget about epochs, episodes, and like evaluation type criterias, and think in a very non-stationary and non-linear way of actually dealing with real life scenarios. And after that, of course, let me know all of the questions that you have in the comments itself. But other than that, these are some of the open questions that I have highlighted. But let's get on with it. All right. This is just going to be like an open discussion of what I think about the paper and how I uh, understood it. So it's not some sort of like tutorial in a sense, but just me spewing my thoughts. So the major topics covered in the paper, of course, we are going to refer the paper in between. I'll just show you that as well. But in the first leg of the paper, we are just talking about intelligence as a signal, as a processing signal over time. And we have different types of signals. In this case, if we imagine a flow or like a framework where we are like working with an agent and an environment, and the observation and the reward itself are like types of signals that we are working towards. So let me just refer to the paper itself for like better understanding. So as you can see, the purpose of this document is twofold, right? You can just go through this once, but we'll try to cover things quicker. And this is what I was talking about. In this case, the observation and the reward both are like types of signals. The observation in this case being the larger sensory signal, while the reward is like the smaller one. But of course, it's like an entire loop. And this kind of setup is common in reinforcement learning. So people familiar with that are able to catch on very quickly. And other than that, let's get on with like the most distinguishing features of this entire plan, right? The first, of course, is the emphasis on ordinary experience. We have to figure out a certain sense of environment which is not fixed. We need to have the complexity of the real world, and we can only have that by having by having uh, a deep understanding of the structure of the world itself. I understand that this paper itself is very abstract in a sense, but this is very important so that we understand the direction towards which AI research should go in the next 5 to 10 years. And let's get on with the next one. I feel that of course, the first feature needs more explanation, but it's still a bit rough in a sense. The second distinguishing feature is temporal uniformity. Temporal uniformity is a way of leaving those epochs, those time steps, and having everything at the same time. You have to understand that these kind of setups require parallelization of all kinds of steps that are being taking that are like taking place, right? There's no special training periods where when training information is available or when rewards are counted more or less than others. They're all equally represented, and they are at every time step. So this is something known as temporal uniformity, having uniformity in the time itself about when the stuff is happening, right? Now, just to cover up stuff quicker, of course, the third distinguishing feature is the computation. If you're aware of Moore's law that says that the number of nodes in a transistor doubles every year, like doubles every few years, we'll eventually run out of compute. And of course, we need to keep in mind the compute power that we have at our disposal as humanity as well. You know, we have to keep that in mind. We have to understand the consideration of computer power. And once we have covered that, just an overview, of course, the fourth distinguishing feature in this case is to focus on an environment that has intelligent agents itself, so that the systems learn how to use intelligence amplification, so that they're able to interact with each other and learn with human to agent or agent to agent interactions. Now, of course, I'll be referring to my notes and whatever I learned from the paper itself, but essentially what I wanted to figure out in these major features. So first, let's talk about temporal uniformity because I feel it needs more clarity. Of course, we need to have such a system which is split in two ways. First are the reactive policies, and the second is the planning in the background. We'll come to that more in some time, so it's all good. Now, let's get on with the major portion in a sense. Once we have set up these kind of constraints, the four constraints or like the four major features, we can then figure out the design around the base agent. What is the base agent based out of? Like, I know it sounds weird, but what is the base agent based out of? There are four key components in a base agent. First is perception. Perception is basically its understanding and like having a past experience or a state. This is a summary that the agent gets. The second is reactive policies. The reactive policies include the primary policy which selects the action that will be sent to the environment. This is basically your sole way to interact with the environment itself. And these policies are essentially, working and get evolution over time. So that is what we need to focus on. Third are the value functions. Now suppose you have multiple options for a task. You want to figure out which one is the best. Value functions help you to evaluate those options itself. And that is how we understand stuff, and that is how the system will know what to choose to do next. Okay. And the fourth component is the transition model. The transition model essentially is like the conglomeration of everything that we came upon till this time. Okay. So in general, the model may be temporarily abstract. That means it cannot take an action but an option and all of that. It basically, if we have a system, an advanced system, and the transition model will be able to evaluate the option and understand what exactly should be the next step forward. The transition model helps to imagine possible outcomes of taking an option. It is able to have foresight of how things will go out. And that's how humans work, right? That's how animals work. And this is the entire thing we're going towards. Now, we need to understand that planning itself is an ongoing process. Now, if we have to plan an action, if we have to plan a workflow, it has to be ongoing. It has to be going in the background at all times. So this is something very important. In the foreground, we have perception, reactive policies, and value functions, the first three features, the first three components. And the fourth component, the transition model itself, is in the background. It is always working. It is always has something going on. Now, of course, you'll have the question of the compute itself, but of course, it's a thing we have to tackle in the future. Once we're done with this, let's get on with how things are going. Okay. Now, we have now understood the base agent, right? Now, there will be multiple things we need to take account into, and we are now going to get into this. This paragraph itself is something that you can pause and read. It is basically like an entire, overview of whatever we have covered so far, and also a few new concepts that will be covered, just name dropping them. And this is the main roadmap to an AI prototype. Now, basically, when you hear the word roadmap, you think that it's like the linear and the correct path that you need to follow, but everything is up to debate. Everything can change, and everything is something that can be reordered. But this is just like a good baseline to work upon, right? So now we're going to cover each and every step one by one to understand what I understood for it. Okay, so of course, representation. Continual supervised learning with given features. Just to give you a quick overview of what exactly we are saying. When we have a very simple system where we are just working with mean square error, or like a simple kind of machine learning model that we are all familiar with, right? We still define the least mean squares error by ourselves. We define the hyperparameters by ourselves. That is something we do not want. What we need to focus on this time is to have meta learning, a meta algorithm. This is something that learns in itself exactly what is going on, right? So this ensures that human intervention is not there, and that is our ultimate goal. We need to have meta learning or meta algorithms that understands the step size, understands the parameters for each feature on its own. Now, what exactly is the reference of the step itself, the first step? The first step is we cannot touch the features. Now, as said in the first step, given features. So, the number of features is something that we cannot meddle with, we cannot touch. And this is the entire thing about. We are going to give the agent the least amount of flexibility that we can possibly, keep it from. So, we need to have least freedom and one of the more tougher questions so that it learns to evaluate on its own with the least amount of tools. It may work very bad, but it's something which is critical for it to understand the workings of a complex system like the world itself. So it may work bad, so it's all good. Yeah, that's like kind of I can't remember the word, but yeah. It's like some sort of poetic device. Yeah, anyway. Representation 2. This is step 2. Now, what's the difference in step 2? Step 2 is where we can create new features. If you remember, the first step included that we should not touch the features at all. The second step, we can create new features, and it gives the system more flexibility to combine features, combine vectors, and to understand exactly what's going on by having more apt features. To understand exactly what's the difference between step 1 and step 2, basically in step 1, the features are fixed, but we can control the importance we give to them, right? So, suppose I need to make this Natraj pencil, okay? Now, when I'm making this pencil, when I'm manufacturing it, I have multiple types of vectors. Suppose we consider the material itself or the color dye on it, right? The material wood or lead or graphite will be given more importance than plastic or metal, right? And the dye red will be given more importance as a feature. Now for this pencil's length is a weaker feature compared to the pencil's how sharp it is. As you can see, it's quite dull right now. So for you to write, it has to be sharp. So that feature has more importance than the length of the pencil. If you get what I mean, like the features are fixed, but we're giving it different importances while learning. In the case of step 2, we can have new features. Okay, we can have things that we can focus on now. Now, suppose I break this pencil and I don't have it now. I can have a new feature where I just bring a new pencil and have a fresh feature set for it. But in this case, the size of the memory is fixed. So you have to discard old features for new features to rise. So this is what the major point is. Now don't worry, like this is like one of the more tougher steps to understand, I believe. but now we're going to cover many of them pretty quickly. So, the step 3, the prediction. Now, this is a way of understanding the complexity of the nature now. As you can see, with each step, we are introducing a new angle of complexity. We are working with linear features in step 1 and step 2. In step 3, we're going to be working with non-linearity and more complex type environments, right? So this is basically it. In step 4, we are going to have the K-arm banded settings. Anyone familiar with reinforcement learning would have an idea, of course. It's just to understand the difference between explore and exploit. Yeah. So that's how you train a model to learn when to explore and when to exploit. Now, another new concept in this step is the actor-critic algorithm. The critic itself does not act. It is not allowed to take the action. The actor only will take the action. But the critic will, of course, as you can learn from the name itself, will critic the actor's actions, and then it will learn over time. The only difference in this case is the critic is not something perfect. It's not a benchmark, it's not a standard. The critic itself is learning as well, side by side along with the actor. So I think you learn and understand what way we are going with, because over time the agent and all its components were earlier very naive, and with each step and each new layer of learning, we are getting more and more mature in a sense. Exactly how an animal or exactly how a human should learn. And let's move forward, right? The step 5 is of course like an add-on to just the step 3, and we just include a new type of reward function basically. And this is something you can just give it a read. It's not that rough. We basically include an average reward function and to understand what exactly is going on, and leverage the system to actually work for our needs. And next is step 6. Again, step 6 is again working on control problems, and this is a way of just tying things up and understanding to test those reward algorithms for learning and planning. And these are the first 6 steps. Now these first 6 steps act as a good baseline over which the next 6 will actually work upon. So let's go on with it, right? So I'm sure that you can understand that step 7 is like pretty normal, I would say. But let's get on with the major one. Step 8. Step 8 is a single step system. It is not allowed to have temporal abstraction. If you remember in the earlier moments of the video, we learned about temporal uniformity. This time we are talking about temporal abstraction. Temporal abstraction basically means to not have options, to not have alternatives. The system will just take one step and it will, it only has the foresight or the imagination to know what will happen in just the next step. Okay. So this is basically it. It forces the system to understand what just the next step will be. It's a single step system. That's why it's a prototype, right? Step 9. Step 9 again introduces more complexity with an asynchronous or a non-linear system. Okay, and it basically it basically repeats itself with just including more non-linearity in the system and in the environment. But regardless, let's get on with step 10, the Stomp progression. This is one of the major takeaways of this paper. As I just said a few minutes ago, step 8 did not have temporal abstraction. So as you can guess, as we're increasing complexity over time, step 10 will have temporal abstraction. It will have the foresight, it will have the options, and it will have the freedom to choose and to plan ahead and to see what could happen next. And the STORM stands for, of course, subtask, option, model, and planning. Subtask. Subtask is also a very important step that we have to introduce. Subtask refers to, of course, a task within a task. Suppose you want to switch on your TV, right? It's not a simple process. It may be simple for humans, but for a system, you have to get to your remote. You have to make sure your TV is on, and then you have to press the remote, and then you have to go to the application you want to go to. If you can break it down, this task of turning on a TV and watching a YouTube video also has multiple subtasks within it. So this is what this system helps to learn. To understand that every task also has its own subtasks within it. Right. Now you can look at this. Sorry, you can look at this diagram over here. It absolutely explains what I'm trying to say. We have the model of options. We have the state features. We have the subtasks to attain features. Then we have the options. Experience is what the agent is seeing. The agent will always ever just see those signals what I talked about in the start. That is all within the agent's experience. Just the observation and just the reward signals. Right? Now, step 11, OAK. OAK stands for options and knowledge. Now, up till step 10, we have introduced Stomp. Okay. The only thing that OAK adds at this point is feedback and to understand what exactly is going correctly. And simply it's a feedback loop where we understand what tasks was going well and what task was not going well, what are the features which are not good and should be discarded, and it's basically a report, and not report as such, but like an evaluation of how things are going. Okay. Now, in these two paragraphs, we basically have like two ways of actually understanding a subtask, and the example given in the paper is like with respect to a keyboard, and each subtask is a chord in the keyboard, and it basically helps you understand in terms of a symphony. Now suppose you press two types of keys at the same time, or two chords at the same time. We're able to merge it and combine it into a new type of sound. So we want to talk about this in like a vector way. We want to press the vector for one feature and the vector for the other feature, and hopefully we can combine it, have a more complex and advanced vector. Step 12 is intelligence amplification. As I've also mentioned in the start of the video, it just basically has agent to agent and human agent interaction settings, and it's like an environment where even humans and animals thrive, like including a social aspect in the agent environment, so that they're able to learn from each other. Now, this in entirety was the crux of the paper, and this is what I understood from it, and this is what my objective at OpenSteam is. So, just to give you like a quick reference to what all happened, the Alberta Plan, the discipline for temporal uniformity, the scaling with the Moore's law, the base agent architecture, the four components of it, perception, reactive policies, value functions, and transition model, and mastering representation, steps 1 and 2, step 3 and step 4, prototypes, the Stomp progression, and lastly OAK. So I would say that this paper actually helps us understand how it is going and how AI research will move in the future. But I hope that during this paper you learned something and I learned something out of it as well. And in the end, hope your mind was steaming after it learned something, and I'll catch you in the next one. Thank you very much.